Hello everybody. Today let us discuss the heap sort algorithm. Heap sort algorithm is used to arrange the elements of a given list in ascending or descending order. Heap sort algorithm is based on the algorithm design technique transform and conquer. Transform and conquer technique has two stages. Initially, in the first stage, it is a pre-processing stage wherein the input elements are transformed to some other form, and in the second stage, the problem is actually solved. So in heap sort, the first stage, that is the transform stage, is to construct a heap, and in the second stage we are going to sort the elements by deleting the largest element from the heap, assuming that we want to sort the elements in the ascending order. So we have to understand these two stages of the heap sort. The first stage, constructing the heap. So we will first try to understand what is a heap. Heap is nothing but a binary tree which has to satisfy two conditions. The first condition is it must be a almost complete binary tree, and the second condition is called as the parental dominance. What is almost complete binary tree, also called as essentially complete binary tree, is a binary tree in which if the tree has height h, then up to the level h minus 1, no nodes will be missing, all the nodes will be present, and in the last level, nodes may be missing, and the missing nodes must be from the right, not from the left. Say for example, if this is a binary tree, okay, and if it has height h, okay, level 0, level 1, level 2, level 3, height is 3. Okay, so up to level h minus 1, okay, up to this level 0, 1, 2, up to the second level, all the nodes must be present. So no nodes are missing here, and at the last level, nodes may be missing, and that must be from the right side. So suppose if this node was missing over here, then this is not a almost complete binary tree, because at the level h minus 1, one node is missing. So if this node is present, then it is a almost complete binary tree. Now suppose if this child was the right child of this node, then it is not a almost complete binary tree, because the nodes that are missing must be from the right. Nodes must be filled from the left, missing nodes must be in the right. So even this is not a almost complete binary tree, because the nodes are missing in the middle. Missing nodes must be present only at the right. Now this is a almost complete binary tree. This is almost complete binary tree. Okay, so that is the first condition, and the second condition is parental dominance. Parental dominance is in the tree, if you take any node, then that node must be optimal compared to its children. What do we mean by optimal? That is, the value of the element present in that node can be either maximum or minimum. Depending on that, we can have two types of heaps. One is called as the max heap, and the other one is called as the min heap. Okay, a max heap is a one in which the elements present at all the levels will be greater than its children. Okay, if you take the root, the element present at the root will be greater than both its children. Next node will be greater than both. At all the levels, the element present at the node will be greater than both its children in a max heap. In a min heap, the element present at the root at the node will be smaller than both its children at all the levels in the tree. We should notice one thing. Heap is a binary tree, but not a binary search tree, wherein the left side element is smaller and right side element is greater, because the element present at the root will be either greater than both the elements or smaller than both the elements. So therefore, heap is not a binary search tree, it is a binary tree. Okay, so now we will try to construct a heap by taking an example. Let us consider we are given n elements, okay, 3, 6, 7, 2, 4, 9, 1, 5, 10, 8. Okay, so let us take these 10 elements and we will see how to make it a heap. So we have to satisfy two conditions if we have to make these elements as a heap. The first one is it has to be the almost complete binary tree. And the second thing is, in the almost complete binary tree, the elements present at all the levels must be greater than both its children. Let us construct a max heap, because let us assume that we want to sort the elements in the ascending order. Okay, so let us assume that these elements are stored in an array called as H. Okay, so first thing is we have to make it a almost complete binary tree. So since it is a binary tree, we may be thinking that using a linked list will be a most efficient way of implementing the heap, but that is not the case. If we store these elements in an array, then it will become easier for us, and representation of this as an almost complete binary tree will be very trivial. How is it? Let us see. Let us assume that these elements are stored in an array named as H, okay, and let us index the array starting from 1, not from 0. There is a reason, I'll tell that later. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 elements indexed from 1 to 10, okay. So now, first thing is, let us make it a almost complete binary tree. How do we make these elements of this array almost complete binary tree is, we will construct a binary tree starting from top to bottom and at each levels inserting the elements from left to right. Okay, so top to bottom, start with the elements present in this array from left to right and construct the almost complete binary tree top to bottom, and at each level insert elements left to right. Okay, so 3 is the first element, first level, so it will become the root. Then the next element will go to the next level. 6 will become the left child of 3, 7 will become the right child of 3, then 2 will go to the next level because this level is almost full, completely full. Okay, next we'll go to the next level, 2, 4, 9, 1. Then this level is completely full, we'll go to the next level, 5, 10, 8. So this is almost complete binary tree. So how can we tell that this is, by looking at this we can tell that this is an almost complete binary tree, but how to correlate this array with this almost complete binary tree and how to make operations. So now if we transform this to a tree like this, then accessing the nodes will become easier. How it will become easier? If you take any node in this particular tree, a node which is present at position I, then its left child will always be present at position 2 into I in this array, and its right child will be present at position 2 into I plus 1 in that array, and the parent will be present at position I by 2, truncating the fractional part that we get. Okay, so we can verify it for any element. So now 6 is present at position 2 in the array. Okay, so now according to this, the left child must be present at 2 into I, that is 2 into 2, 4. Okay, so 2 into 2, 4. So the left child is 2 and 2 is present at location 4 in the array. Right child must be present at 2i plus 1. So 2 into I is 2 into 2, 4. 4 and 4 plus 1, 5. Okay, element 4 is present at position 5 in the array. Okay, and its parent must be present at I by 2. So this is present at position 2. Parent must be present at 2 divided by 2, that is 1. So if you can see 3, which is the parent, which is present at position 1 in the array. So therefore you can verify it for any element present in this tree. The left child will always be present at 2i, right child at 2i plus 1, and parent at I by 2. So therefore, if we represent the elements, input elements in an array and index it from 1, accessing these elements will become easier, and therefore writing an algorithm will be very simpler. Okay, so the first condition is satisfied. We have made the input elements almost complete binary tree. The next thing for us to do is parental dominance. That is, elements present at every level in the tree must be greater than both its children, because we want to construct a maxing. Say for that matter, element present here must be greater than these two, element present here greater than these two, element present here greater than these two. Like this we have to make sure. And to do that, we can make one more observation, that is, in a almost complete binary tree that consists of n elements, the upper half of the n by 2 elements will be parents, and the lower half of the n by 2 elements will be leaves. Okay, so leaves means they will not have any children, therefore parental dominance does not apply to the lower half of the elements present in this array. So we have 10 elements, the first 5 elements 1 2 3 4 5, so these 5 elements will be parents wherein the parental dominance has to be checked, and the next 5 elements will be leaves which will not have any children, therefore parental dominance does not apply. Say for example 9, okay, 9 is present in 6th position, it doesn't have any children. 1 doesn't have, 5, 10, 8, so we need not apply the parental dominance to these leaves. So the parental dominance has to be checked for the first 5 elements, 3, 6, 7, 2, 4, first 5 elements in the almost complete binary tree. Okay, so this process of now making each one of the nodes larger than both its children, that is transforming this to be a heap, is called as heapify. So now we are going to heapify this particular almost complete binary tree. So how do we do that? So to do that, once again there are two algorithms. One is called as the bottom up heap construction and the other one is called as the top down heap construction. In the bottom up heap construction is the one that we are going to do because it is more efficient than the top down heap construction. Okay, so let us discuss the bottom up heap construction. In bottom up heap construction, what we do is we will start with the last parent and we will go towards the first parent. Okay, so which is the last parent? There are 5 parents over here. The 5th one is the last parent. So from 5th we move to the 4th parent, then to the 3rd parent, then to the 2nd parent, and then to the first parent. So in this particular fashion we are going to heapify the nodes. Okay, so what do we mean by heapify? We have to make the node present at element present at that node larger than both its children. How do we do this? So to do this, what we can observe is every node will have 2 children because it is a binary tree. So we have to compare the 3 elements and the largest one should come to the parent. How can this be done? We can consider any one of the elements as largest and compare with the other 2 elements and bring that largest element to the root. But to have a very efficient implementation, what generally we do is first we will find out the largest child. Which child is larger, whether the left child is larger or the right child is larger. Once we know the largest child, then we will compare the largest child with the element present at the root. If the element present at the root is greater than the largest child, then this subtree means from this node all the nodes that are present below is a heap. Okay, if that is not the case, then we have to heapify. Okay, so this is the idea. So we will see how we are going to do that. Okay, as I have already told you, we will start from the last parent. Okay, so the last parent is 10 by 2, that is 5. 1, 2, 3, 4, 5. So we will place one pointer I. Okay, we will also place another pointer k. I'll tell you why little later. Okay, and now as I told, first we will find out the largest child. Okay, when we have to find the largest child, first thing what we have to make sure is that this particular node has children. Okay, so if it has children, even though it doesn't have a right child, it will at least have a left child if it has one child. Okay, so therefore first we will check whether it has a left child. Yes, it has a left child, so we will place one pointer to the left child assuming that this is the largest child. Then we will compare the left child with the right child. In our case there is no right child, so since there is no right child, this is the largest child. Okay, and this largest child we compare with the parent. Okay, so when we compare the largest child with the parent, we notice that the parent is not greater than the largest child. Therefore, this element must occupy this position. But whether 4 should come here, should we swap 8 and 4? Actually, we are not going to swap 8 and 4. Once again, to improve the efficiency of the entire algorithm, what we do is, I will tell you a little later why we are not doing that. 4 will be copied to a temporary variable, say b, and the largest child will be brought to the root. The reason why we are not copying 4 here is this tree may be having some more levels. As we go up, this node will have more levels, 1, 2, 3 levels. Okay, in this case it is not there, but I am giving you the idea. So if this has children, suppose if this has children, then the elements present as their children, one of them may be greater than this element 4. So if that is the case, that element has to be brought here and this will go further downwards. So that is the reason why we are not going to copy the parent to the child. Only the largest child will be copied to the parent, and this will be copied to some temporary variable. After copying this to temporary variable, this k will be moved to the place wherein this element was supposed to be copied. So this element was supposed to be copied here, so k will be pointing here. I will anyways be here itself to tell that this is the parent that we are heapifying. Once we heapify this, we need to move to the next parent. Okay, now we will come here and we will see whether this has children, left child. No, it doesn't have any children, therefore there is nothing for us to move downwards. Therefore this 4 will be copied to this particular location. Okay, so for time being, just understand this. Next, after the 5th parent, we move to the 4th parent. So 4th parent, we place the pointer I here. Okay, k, 2 pointers we place. Okay, and the value we copy it to v, this value, because later we'll have to move it down. Okay, so j pointer will be placed to the left child. Left child is 2 into k. Okay, 2 into k will be the left child, 2 into k plus 1 will be the right child. Okay, so 2 is present at 4, 4 2s are 8. At 8 location we have the left child. Okay, left child we place a pointer j. Left child is compared with the right child, and we find out that right child is greater than the left child. Therefore j pointer will move here, telling that this is the largest child. Okay, now the largest child is compared with the element present at its root. So we find that root is not greater than the largest child. Therefore 10 will be moved to the root, largest child will be moved to the root, but this element will not come here because this may have children. So to do that, what we do, we bring k here. Left child will try to place, there is no left child, therefore that ends there, and 2 will be copied here. So 4 is epified, 5 subtree rooted at 5 is epified, subtree rooted as 4 is epified. Now we will move on to 3, subtree rooted at 3. We will place the k pointer, j pointer to the left child. Left child, when it is compared with the right child, we conclude that the left child itself is larger. Now we will compare 7, we copy to a temporary variable. When we compare the largest child with the parent, we notice that parent is not greater than the largest child. Therefore the largest child will come to the parent's position. 7, which was supposed to come here, k pointer will be moved there, and j will be placed to its left pointer. There is no left child, therefore 7 will be copied here. Parent 3 is epified, this subtree is epified. Now we will move on to parent 2. So that is why I always tells which is the parent that is epified and which parent we need to go next. Okay, so I is placed at the second parent, v is 6, k will be placed here itself initially, j will be placed to the left child. Okay, when we compare the left and the right child happens to be greater. Okay, so therefore j pointer remains here itself. We will compare this with the parent. Okay, now we will notice that the element present at the root is not greater than the largest parent. Therefore 10 will be copied to the root. 6, which was supposed to be copied here, is not copied still because it also has children. Okay, so now therefore this k pointer will move to the position where the 6 was supposed to be copied. 6 was supposed to be copied here, we have not copied. K will move there. Okay, and j will be pointing to its left child. Left child will be compared with the right child. Left child is larger. This, when it is compared to the element that was supposed to be at the parent, that is 6. 6 is already greater than 5. So therefore 6 will be copied here. And this subtree rooted at 10 is a heap. Means this is larger than its children. This is larger than its children. This is larger than its children. So therefore this subtree is a heap. And finally we move to the first parent. Okay, so now k pointer will be pointing here. This will be copied to a temporary variable. Okay, so j will be pointing to the left child. When we compare the left and the right child is greater. So therefore we will compare the greater child with the parent. Parent happens to be smaller than the largest child. Therefore 10 will be copied here. 3 is not copied here because we need to make sure that this is also a heap, because already we have made this a heap, and now when we swap the elements, that parental dominance condition should not be violated. That is the reason why we don't copy 3 here, and here you can see if we copy 3 here, the parental dominance at this particular position will be violated. So therefore now we will the location where 3 was supposed to be placed, to that place we will bring the k pointer and j pointer to its left side, okay, to star k. Okay, so left child when it is compared with the right child, we find that right child is greater, therefore j will move to point to the largest child, and when the largest child is compared with the element that was supposed to be at its parent, okay, we find that the element present at the root is smaller than the largest child, therefore 8 is moved here. Okay, now you can see if we had copied 3 here, then again we should have made a swap. To avoid this swap, we are storing it in one temporary variable, and now 3 which is supposed to come here is not stored there. Okay, so again the place where 3 is supposed to be copied, we move the k pointer and we place the j pointer as its left child. Okay, because this subtree we should see whether it is a heap or not. Okay, and now when we compare, there is no right child, this is the largest child. When we compare the largest child with its root, the element that is supposed to be at the root, we find that the element present supposed to be at the root is not greater than the largest child. Therefore, this will occupy the root's place and k will come here where this element is supposed to be copied. When we try to place the j pointer to its left child, we will notice that there is no left child. If it doesn't have left child, no question of right child. Therefore, 3 will come here. So now we can see the first parent is heapified. That is the reason why we have 2 pointers I and k. K keeps moving downwards as we heapify at the higher levels. We need to move to the lower levels. Therefore, I will tell which is the parent that we are heapifying currently, and since the first parent is heapified, the entire tree is a heap. Okay, already it was almost complete binary tree when we stored in an array. Now we can see at every level the element present at the root is greater than its children. Okay, you take any parent, we will take the last parent. 4 is greater than 3, 6 is greater than these two elements, 8 is greater than these two, 9 is greater than these two, 10 is greater than these two. So therefore, at every level, the elements present at each and every node is greater than both its children. Therefore, this is a heap now. This is a heap. So one thing we can observe in a heap is the element present at the root will be the largest if we are constructing a max heap. If we are constructing a min heap, the element present at the root will be the smallest. Okay, so we can't tell the same thing about the other nodes. We can't tell that the second largest element will be present here, third largest will be present here. As we can see here, 8 is not the second largest among these 10 elements, it is 9. So therefore, we can't make any such assumptions about the elements present in other places. Only thing that we can tell is the largest element is present at the root. Okay, among all the n elements, the largest will be present at the root. Okay, so now this is the heap. The first stage of heap sort is done. Okay, what is the next stage? The second stage is, as I told, deleting the root. Okay, how do we delete the root and what do we mean by deleting the root? So what we basically do to delete the root is, among the n elements that are present, we will swap the root with the last element. So the last element is the 10th element. We will swap these two elements, and after swapping, we will assume, logically, we will assume that this element is deleted, and for us, we have only 9 more elements left. Okay, so how do we represent it? 3 will come to the root. All other elements will remain in the same place. 8, 9, 6, 4, 7, 1, 5, 2, and 10 is will come here, and since we want it to be logically deleted, we will represent it by a dotted line and we write 10 here. So logically 10 is deleted. Okay, and we have only 9 elements. Why we are doing this is, as I already told, how we can represent the elements in this array into a almost complete binary tree. Now when we represent the elements of this almost complete binary tree back to the array, the elements will be in this particular fashion: 3, 8, 9, 6, 4, 7, 1, 5, 2, 10. So now you can see the largest element has occupied its final sorted position. So 10 is the largest element, it has gone to the last position. So therefore, we will take only the remaining 9 elements and we are going to repeat the process so that all the elements will be sorted. So this is one pass of heap sort algorithm. So in subsequent passes, what are we going to do? So now one thing what we can observe is, when we exchanged the largest element with the last element of the list, at this point the heap parental dominance property was violated. So therefore what we do is we will place the k pointer over here and we will heapify it from here downwards. Okay, so once again, like we did earlier, k is here, j will be placed to the left child. We compare the left child with the right child. Right child happens to be greater, so therefore j pointer will be moved to point to the right child. When we compare the right child with the largest child with the parent is smaller than the largest child, therefore this is copied to a temporary variable. 9 is moved here, 3 which is supposed to come here. Now we have to check whether it has some children which are bigger than 3. So therefore k pointer will be pointing here where 3 is supposed to be copied, and j will be pointed to its left child. When the left child is compared to the right child, left is larger. When the larger child is compared to the element that is supposed to be present here, that is 3, we find that 7 is bigger than the element supposed to be in the root. 7 will be copied here. It doesn't have a left child, therefore 3 will come to this place. Okay, and now when we move the 3 downwards, it came to the right part of the tree and the left part of the tree is unaffected. Therefore this will be a heap. Already it was a heap, so this subtree will always be a heap. This will not be affected, so only the right part is affected, and that also we have made a heap. So now once again this subtree, which consists of 9 elements, is a heap. Okay, and among them the largest one, that is 9, has occupied the roots position. So what we do is we again delete the root. Okay, exchange it with the current last element present in the tree. So the current last position is this, so 9 and 2 will be swapped, so therefore 2 will come to the roots position. 8, 7, 6, 4, 3, 1, 5, 9, 10. So these 2 elements are deleted now. We have only 8 elements left. We need to heapify this. So once again, k, left child compared with right child, left is larger. 8 compared with the root, this is larger. Root element is not larger, therefore 8 will come to the root. 2 will not come here. Instead, k will come to that position. J pointing to the left child compared with the right child, this is larger. This compared with element supposed to be here, that is 2, this is larger. 6 will come here. 2 will not be copied here, it will be checked with its children, therefore k will be placed here, j will come here. 5 when it is compared here, we find that 5 is larger, therefore 5 will be copied here, and when we come to this level, we find that there is no left child, so therefore 2 will be copied in this particular location. Okay, and this is how we are going to heapify. Okay, so now again we will delete 8, means swap 8 with the current last position that is available. Okay, so when we do that, 2 will come to the root. 6, 7, 5, 4, 3, 1, 8, 9, 10. So even though the tree has 4 levels, the last level is logically deleted because all the 3 elements got deleted. So now once again we need to heapify this. K, left child, right child is greater, so j will point here. Right child, when it is compared with the root is smaller, therefore 7 will occupy this position. 2 is here. Okay, 2 which was supposed to come here will be compared with its children. Left child, j will come here actually, sorry, k will come here. So when 3 is compared with 2, 3 happens to be larger, so 3 will be copied to the roots position. 2 has to come here, so k will come here. There is no left child, therefore 2 will be copied here. Okay, now among the 7 elements, the largest element is 7 and that occupied the root. So once again we'll have to delete. This is the last element now because 8, 9, 10 position elements are deleted. Only 7 elements are present in the array. So we'll swap it with that. 1, 6, 3, 5, 4, 2, 7, 8, 9, 10. K, J, When it is compared with the right child, this is the largest child. When the largest child is compared with the root, 6 will occupy this position. 1 was supposed to come here. Therefore, we will move k here. Left child j, this is larger. Compared with this, 5 happens to be larger. 5 here, and 1 was supposed to come here. We are not going to copy it yet. K will be moved here. When we check whether it is a left child, logically the left child is deleted. There is no left child. Therefore, 1 will come here itself. Okay. So among the 6 elements, the largest element is 6, and that is present at the root. The current last position is this. So 2 and 6 will be swapped, and at every stage you can observe that wherever the node moves, the other part is untouched. Therefore, that is a heap. 7 is already deleted. So this part is a heap. Okay. So when we swap 2 and 6, 2 will come here. 5, 3, 1, 4, 6, 7, 8, 9, 10. K, J, this is the largest child. When we compare, parent is smaller, 5 will come here, 2 was supposed to come here, its child, J is pointed here, K will be pointing here. So this is the largest child, J will come here. When we compare 4 with 2, 4 comes to the root, and 2, its child is already deleted, therefore 2 will come and sit here. Among the 5 elements, 5 has come to the root. Okay. So this will be swapped with this. 2, 4, 3, 1, 5. I will not write the rest of the elements. Okay. So K, J. This is the largest child. When you compare 4 with 2, 4 is the largest child, 4 will come here. 2, which was supposed to come here, will be compared with its child. It's already larger, therefore 2 will come here, it will not be compared with its children. Okay. Now 4 will be swapped with this, and therefore we have 1, 2, 3, 4, 5. Rest of the elements already deleted. Okay. K, J. When the children are compared, right child happens to be greater. When the largest child is compared with the root, this is larger. 3 will come here. No children. 1 will be copied here. Okay. Now the last element is this. Therefore, 3 will become swapped with this. 1 will come to the root. 2 is here. 3 will come here. All the other elements are deleted. K, J. Largest child. This element is smaller than the largest child. So 2 will come here. This doesn't have any children. 1 will come here. Okay. Now we have to swap. So when we swap, 1 comes to the root. 2 comes here. 3 is here. Okay. And this element we don't have to do anything. When there is only one element, we don't have to heapify because that is the only element present there. And all the other elements which we didn't write till now, if we write, then the tree will look like this. Okay. All the elements are deleted except the first element, but they are there, actually there in the array. When you write it in the array, we have to write it top to bottom, left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the elements are sorted. So this is how heap sort works in 2 stages. The first stage is heapification stage and the second stage is deletion stage. Okay. So now let us try to analyze the efficiency of heapification. What is the efficiency of heapifying a almost complete binary tree? So the first thing is, what is the input size? The input size is nothing but the number of elements present in the array, that is n number of elements. Okay. And what is the basic operation that we consider? Based on what operation are we going to analyze the efficiency of the algorithm? So we can see for doing it almost complete binary we are not doing anything. Only for EPifying we are comparing the elements and then bringing the largest element to the root. So this comparison operation is being done extensively, once to find the largest child and then to find out whether the root has to have the same element which was there earlier or the element the largest child has to occupy. So basically among these three nodes at any point of time we will be doing two comparisons. Okay, so therefore we will consider the key comparison operation itself as the basic operation. Okay, key comparison operation. So how many times are we going to perform the key comparison operation is what we have to find out. Whether the heapification process has best case and worst case and average case, yes, it does have best, worst and average cases. Okay, so in each one of the cases we need to find out how many times, the count of number of times the key comparison operation is performed, C of n, how many times the basic operation is performed. So when will the best case and worst case occur in a heapification process? Okay, so for that, in the worst case, let us assume that instead of an almost complete binary tree, the tree is a complete tree, binary tree. It is a tree which is full. Okay, even a complete binary tree is almost complete binary tree. Okay, so let us consider it is a complete binary tree and let us see how many number of times the comparison operation is performed, key comparison operation is performed. So one thing if we can observe, at every level, now this is a binary tree, okay, whose height is 1, 2, 3. Height of the tree we represent by h, it is equal to 3. Okay, and this is level 0, this is level 1, this is level 2, this is level 3. Okay, at the last level, that is at the level h, okay, level 3, we are not going to do any comparisons because it does not have any children. We are not going to check with the largest child and all these things. We are not going to do at the last level. But leaving this last level, from the previous level up to the first level, we are going to do the key comparison operations always. How many times are we doing the key comparison operations? If you observe, when we take any node, we will be doing two comparisons. We will be doing two comparisons with the children ones and with the root ones. So two comparisons for this node. Okay, so now at this level, level 2, we will be making two comparisons and the largest will come here. Here also two comparisons, here also two here also two comparisons, here also two comparisons will do. Okay, now when we come to this level, how many comparisons are we going to do? So here we are going to do two comparisons. After doing two comparisons, the largest element will be brought to the root, but this element will not be brought to the child. To bring it to the child, we will come one more level downwards and we will compare it with its children. We will compare it with its children. So once again to compare here, we will be doing two more comparisons. Okay. So therefore, as we move higher up the levels, as many levels are there below, at each one of the levels, we will be doing two number of comparisons. In this level we will be doing two comparisons and in this level we will be doing two comparisons, because every time we will be taking one path and the other paths will automatically be eliminated. But at least we will be doing two comparisons. For this, two comparisons at this level, and we come down this level either here or here, we will be doing two comparisons, and here we are not going to do anything. Okay, same thing here. When you come here, two comparisons for this level, either you go here or here. At this level, two comparisons, either you go here or here, you come here, two comparisons at this level. So three levels. For three levels we will be doing two comparisons. At this level, for two levels we will be doing two comparisons. Here only one level, two comparisons will be doing. So how to account for this? Okay, so all the nodes present in this level will be doing two comparisons. All the elements present here will be doing 2 into 2 4 comparisons. All the elements present here will be doing 2 into 2 number of comparisons. Okay, now if you can see, we have found out the height of this. Okay, and these are the levels what we have written. Okay, if we can see, at this level we are not going to do any comparisons. Here 3 minus 2. Okay, so in this level, one set of two comparisons each we will be doing for all the nodes present here. When you go to the next higher level, okay, this is level 1, 3 minus 1. Okay, means one set of two comparisons for this level, one set of two comparisons for this level. So two sets of 2 comparisons each. When we go to this level, level 3 minus 0 is 3 sets. One for this 2 comparisons, then we'll come to one of these levels, 2 comparisons, then we'll come to one of these levels, 2 comparisons. So 3 sets of 2 comparisons each. Okay. In this level, we'll be doing 3 minus 0 number of comparisons. Here we'll be doing 3 minus 1 number of comparisons. Here we'll be doing 3 minus 2 number of comparisons for all the nodes. Okay. So we have accounted for how many comparisons will be done at each level. We have not accounted for how many nodes are there at each and every level. Okay. So first thing is we will be doing h minus I 2 times h minus I number of comparisons. If you are at level 2, 3 minus 2, 1 into 2 number of comparisons. If you are in level 1, 3 minus 1, 2 into 2 number of comparisons. If you are in level 0, 3 minus 0 is 3 into 2 number of comparisons we are doing. Okay. How many nodes are there? So here there is only one node, here there is 2 nodes, here there are 4 nodes. If there is some more levels, here there are 8 nodes, here 16 nodes. So how do we get the number of nodes present at each and every level? We can see at each and every level, if we represent the levels by I, okay, here that is what we have taken, this level, h minus I, h is the height, level is 2, okay, we have taken it as I. So if we take any level, there will be 2 to the power of I number of nodes. At level 0, 2 to the power of 0, 1 node. At level 1, 2 to the power of 1, 2 nodes. At level 2, 2 to the power of 2, 4 nodes. At level 3, 2 to the power of 3, 8 nodes. So in this particular fashion it increases. So therefore we need to do these many multiplications for each one of these nodes, each one of the 2 to the power of I nodes that are present in the worst case. So that is what we have to find out. So therefore in the worst case, the number of comparisons that we do will be summation I is equal to 0 to h minus 1. 0 to h minus 1, because in this level we are not going to do any comparison operations. Okay, how many comparisons will be doing? 2 into h minus I number of comparisons at different levels, and at each level there are 2 to the power of I number of keys. At each level there are 2 to the number of I keys. For each one of the keys, how many comparisons we are doing? H minus I number of levels below it. At each level, 2 comparisons. Okay, so this is how we get the worst case of heap sort. Okay, so now when we solve this, I'll write it down again here. C of n is equal to summation I is equal to 0 to h minus 1, 2 into h minus I into 2 to the power of I. Okay, so this we have. What we'll do is we'll multiply this, okay, 2 into h into 2 to the power of I. Okay, so therefore we'll get it as summation I is equal to 0 to h minus 1 h into 2 into 2 to the power of I. So it will be 2 to the power of I plus 1 minus 2 into I into 2 to the power of I. So it will be 2 into I into 2 to the power of I. Bracket has to come to the whole thing. 2 into I into 2 to the power of I. So now we'll apply this summation separately for these two components. So therefore we'll get it as that is equal to summation I is equal to 0 to h minus 1 h into 2 to the power of I plus 1, okay, minus 2 summation I is equal to 0 to h minus 1 2 into I into 2 to the power of I. Okay, so here we can bring h outside. Okay, h into summation I is equal to 0 to h minus 1 2 to the power of I plus 1. Here we can bring 2 outside, minus 2 times summation I is equal to 0 to h minus 1 I into 2 to the power of I. Okay, we have formulae for summation I is equal to 0 to n 2 to the power of I and I into 2 to the power of I. Okay, so that is summation I is equal to 0 to n 2 to the power of I is equal to 2 to the power of I plus 1 minus 1, and summation I is equal to 0 to n I into 2 to the power of I is equal to n minus 1 into 2 to the power of I plus 1 plus 2. So when we apply this formula over here, okay, so for this when we apply, okay, we get this h into 2 to the power of I plus 1. So for 2 to the power of I plus 1 we have to apply this. So this will become, in our case the I is ending at h minus 1, therefore it is 2 to the power of h minus 1. For this I, this plus 1 is this plus 1 and another plus 1, because the formula has one more plus 1, okay, minus 1, okay. So that is the expansion for this, minus 2 into I into 2 to the power of I. Here also I is ending at n, but our n is ending at h minus 1, so therefore n minus 1 will be h minus 1 minus 1, okay. N itself is h minus 1, so h minus 1 minus 1, 2 to the power of I is h minus 1 plus 1, okay. 2 to the power of I is h minus 1 plus 1 plus 2. So this minus 1 plus 1 gets cancelled, this minus 1 plus 1 gets cancelled, okay. So now when we remove the brackets, h into 2 to the power of h plus 1 minus h, okay, minus 2, this is 2 to the power of h into 2 is 2 to the power of h plus 1, okay, into h minus 2 plus 2, okay. So this further we can remove the bracket, so when we remove it is h into 2 to the power of h plus 1 minus h into 2 to the power of h plus 1. Then again when we multiply this 2 to the power of h plus 1 with this 2, we will get it as plus 2 into 2 to the power of h plus 1 plus 2, okay. This h into 2 to the power of h plus 1 minus h into 2 to the power of h plus 1 will get cancelled. This 2, this we will get it as 2, this is 2 to the power of h plus 1, so therefore we can bring out one more 2 and multiply with this 2 squared into 2 to the power of h minus h plus 2, okay. So now the height of the tree, we took h as the height of the tree. So since it is a binary tree, what will be the height of the tree? If there are n nodes in the tree, then the height of the tree will be log n to base 2, okay, or n is equal to 2 to the power of h. In our tree it is a complete tree, therefore number of nodes is equal to 2 to the power of h, okay. So therefore now we will substitute that value. So here we have 2 squared into 2 to the power of h, so we have 2 to the power of h, therefore we have to take logarithmic over here. So when we take logarithmic over here, we will get it as 2, and this 2 to the power of h we get n. Log 2 squared is nothing but 2, log 2 to the power of h is nothing but n, minus h we have log n to base 2 plus 2, okay. Now we can eliminate all the lower order terms and constants. 2 will eliminate, log n is a lower order term, 2n, so we can eliminate this 2 also, and therefore the worst case efficiency of heapifying belongs to linear class, theta of n. So this is the worst case of heapifying, heap bottom up heapification, that is linear. If we see the best case of heapification, when will the best case occur? In the best case, what happens is, see, when will the best case occur? Best case occurs when we will not have to swap anything, okay. You compare element present here with the children, this is already larger than these two. Here this is larger than these two. Here this is larger than these two. Once this is larger than these two, there is no question of going to the down levels. Two comparisons will be done here, but we need not go down one more level and compare it with its children, okay. So therefore in the best case what happens is, for all the parents, as soon as you compare it with the children, you will have to do two comparisons anyways, to find the largest child and compare it with the parent. After doing those many comparisons, it will already be a heap. So therefore we need not go to the lower levels. So how many ever levels be there, even you come to the root, even if there are 100 levels, as soon as you compare it with two children, this is larger and everything below it is a heap, therefore we stop it there. Okay, so therefore what happens is at every level we'll be doing only two number of comparisons. Okay, so in the best case, what happens is for all the parents we'll be doing two comparisons. How many parents are there? We have already seen that there are n by 2 number of parents. Okay, and for each parent we will be doing two number of comparisons. So therefore even the best case will belong to theta of n, linear efficiency. Okay, so therefore both the best case and the worst case of Heap Sort algorithm belongs to linear efficiency class. Okay, so let us quickly look at the algorithm of for heapifying, heap bottom up. Okay, so we will have an algorithm named as heapify, which will take the array H, indexed from 1 to n. Okay, indexed from 1 to n. We have a for loop which runs from the last parent down to the first parent. This is what we did. Okay, what we do, first we will copy the value that is present at the root to, first we will place a pointer k also at I. Okay, and we will take the value which is nothing but h of k. Okay, and initially we will assume that the heap is false, means it is not a heap. Now what we do is, until we make it heap, while heap is not equal to true, as long as it becomes a heap. And the next thing is, what has to happen is, there must be a left child for us to proceed. The tree that we have must have at least a left child, if not both the children. Okay, j is less than or equal to n. So if it has a, not j, k is less than or equal to, k is the node at any level, 2 star k is the left child, that must be less than or equal to n. So if it means that this particular tree has a left child wherever we have placed k we have placed at I, from I to star k, that is it has a left child. Okay, so now once we make sure that it has a left child, we will place the j pointer to the left child. Once we place the j pointer to the left child, we want to check whether it has a right child also. So therefore what we do is, if j is less than n, okay, if j is equal to n, it means that that is the last node and that happens to the left child, therefore there is no right child. If it is less than n, it means that there is at least one more element, and that one more element can be the right child, definitely has to be the right child. So since it has a right child, now we have to compare which child is greater. If h of j, wherever j is pointing to, happens to be less than h of j plus 1, the right child, okay, then right child is greater, therefore we have to move the j pointer to j plus 1, okay, and k will come down to wherever j was pointing. Sorry, j is moved to the right. Okay, now once we move the j to the right, we need to compare whether the element present at the root is bigger than the largest child. If h of k happens to be greater than or equal to h of j, so if the parent happens to be greater than the greatest child, then heap is equal to 2. We have achieved the heapification. Else what we have to do, we have to move the largest child to the parent, that is h of j will be moved to h of k. Parent will get the largest child and parent will come down wherever k was pointing. Okay, so parent will come down. So from there, once again it will come to the top of the while loop. It is not a heap. Once again from there it will check whether it has a left child, if it has placed the left pointer there. So this process keeps happening. Once it finds the last position where the node can be placed, then this value which we have stored here temporarily will be moved to h of k is equal to v. So this is the algorithm for bottom up heap construction, EP5. Okay. So we have already in the beginning we have discussed. So heap sort algorithm has two phases. One is EP5 we saw, and the second phase is only a small thing, that is we need to delete. We need to swap h of 1, always the root element, and h of n minus 1, means every time the n value will keep decrementing for I is equal to 1 to n. Okay, so we will keep deleting we'll swap the first and the current largest element. Okay, and then after doing that we will keep EP5 h of n minus 1. Okay, so this is heap sort algorithm. We have to swap with the current largest element, and we have to EP5 the array of size 1 smaller than whatever was earlier. What will be the efficiency of this heap sort algorithm? So the efficiency of heap sort algorithm depends upon the heapification process and this deletion. Okay, so now heapification we have already seen. If we use bottom up heap, the efficiency of heapification is theta of n. Okay, now plus for deletion, what will be the efficiency of deletion? Okay, because after deleting, once again will be heapifying. Once again will be heapifying, starting from the root till the bottom level. And once again here also in the worst case, the element that is swapped to the root might move from here till the leaf. Okay, what will be the efficiency of this? And as we have already discussed, even though the element moves from the root till the leaf, it will be moving in only one part of the tree, and the other part of the tree will remain unaffected. So therefore, the movement of the element from the root till the leaf happens only for the height of that particular tree. So what is the height of the tree? So the height of the tree is log n to base 2. Okay, so that we know. Height of the binary tree is log n to base 2 in the worst case. Okay, so therefore, how many times will we be doing these deletions? We will be doing the deletion n minus 1 times. We'll be doing the deletion n minus 1 times. Okay, so therefore, summation I is equal to 0 to n minus 1, or put it in other terms, log n minus 1 to base 2 when we do it for the first element. Okay, plus log n minus 2 to base 2 when we delete the second element, plus log n minus 3 to base 2. This we keep on doing until we get log 1 to base 2. Okay, log 2 to base 2, because log 1 anyways will not be there. For one element we are not going to do any swapping, so that is nothing but, and this is the height of the tree. At each level we will be doing 2 comparisons. Okay, we will start here 2 comparisons, and depending upon the height of the tree, at every level 2 comparisons will be done. 2 comparisons for the first element log n minus 1, 2 comparisons second time when we delete second pass, third pass, fourth pass, so on and so forth. So this is summation I is equal to 1 to n minus 1 log I 2 times. Okay, so this, when we for this there is a formula. Okay, we have the formula summation I is equal to 1 to n log n to base 2 is equal to n log n. Okay, n into log n to base 2. So now when we apply that to this, we will get it as our n ends at n minus 1. It is n minus 1 into log n minus 1 to base 2. Okay, so therefore when you simplify this, you will get it as n log n minus 1 to base 2 minus log n minus 1 to base 2. lower order term is this log, and therefore the efficiency of heap sort algorithm, if we use this bottom up heap, is belongs to n log n. Okay, so this is the efficiency of heap sort algorithm, because in both the cases the efficiency of heapification is theta of n. Okay, and here we have n log n, so therefore the efficiency of the heap sort algorithm is, this is the heapification process plus n log n. So this is nothing but, once again the lower order term goes off, and therefore the overall efficiency of heap sort algorithm will belong to n log. This is the efficiency of deletion. This is only the efficiency of deletion. So when we are doing deletions every time, what will be the efficiency? So that is n log n. Heap sort's efficiency is efficiency of heapification plus deletion. So theta of n plus n log theta of n log n. Okay. So n is a lower order term, it gets cancelled, and the efficiency of heap sort is n log n. Thank you.